This is ELC 131, Circuit Analysis 1, and this presentation is on transformers. Now, Figure 1 shows the construction of a basic transformer, and it's merely two coils placed such that the flux that's created when current flows through one of the coils induces a voltage in the other coil. The coil that we apply voltage to is the primary current. The coil where we obtain the induced voltage is the secondary coil. Now understand that a transformer can only operate with an alternating current source so that the magnetic field expands and contracts, or a changing DC voltage. So again, the magnetic field expands and contracts. A transformer will not or cannot operate with a steady state DC voltage applied to the primary. Now the schematic symbol for a transformer is shown in Figure 2, merely two coils placed in parallel with one another as shown. However, you may see some schematic symbols as shown in Figure 3, which designate an iron core. Now, a transformer again is constructed with two coils placed such that the flux that is created by current flow through one coil induces a voltage in another coil. And the way this is done is that we wrap both the primary and secondary coils around a core, an iron core traditionally, as shown in Figure 4. Now they do this so that the flux that's created by the primary current will stay inside the core and not just go out into space. And this core is nearly always constructed of laminations, and they do this to reduce the losses due to eddy currents. Now, the most fundamental quantity that we use to describe the operation of a transformer is the turns ratio. It's also referred to as the transformation ratio. And this simply states the ratio of the number of turns in the primary coil, NP, and the number of turns of wire in the secondary coil, called NS. And this ratio of NP to NS also gives us the ratio of voltages in the primary and the secondary. So as seen, NP over NS equals VP over VS. Now, if we assume that the transformer is 100% efficient, we can state that the power delivered to the primary is equal to the power that can be delivered by the secondary. And with P equaling V times I can state this as VP times IP equals VS times IS. And let's put all the V's on one side of the equal sign and all the I's on the other side of the equal sign, and we get that NP over NS again equals VP over VS, which equals IS over IP. So note there's an inverse relationship between the primary and secondary voltages and the primary and secondary currents. Now, I've seen some books, textbooks, that describe the transformation ratio of a transformer as being symbolized with the lowercase letter a, which is given as IS over IP. However, I will use the capital letter N for the transformation ratio, which again states the ratio of the voltages in the primary and the secondary. Now let's look at an example of a transformer. For the transformer of figure 5, we're given that 120 volts is applied to the primary. What is the secondary voltage? Well, we start with our equation, MP over NS equals VP over VS. We substitute our known values. There's 10 turns of wire in the primary. There's 2 turns of wire in the secondary. The primary voltage equals 120 volts. So we calculate the secondary voltage to be 24 volts. Let's look at another example. For the transformer of figure 6, we're given that the primary voltage is 120 volts. And what is the secondary voltage? Again, we start with our equation, NP over NS equals VP over VS. We substitute our known values. NP is 2, NS is 8, and VP is 120 volts, and we calculate the secondary voltage to be 480 volts. Now let's look at a calculation to determine the secondary current. So for the transformer of figure 5, we're given that the primary current is 100 milliamps, and we're asked to find the secondary current. Again, we start with our equation, NP over NS equals IS over IP. We substitute our known values. NP is 10, NS is 2, and IP is 100 milliamps. And we solve for IS equals 500 milliamps. And one more calculation or example. For the transformer of figure 6, we're given that the primary current is 2 amps, and we're asked to determine the secondary current. We start with our equation, NP over NS equals IS over IP. NP is 2, NS is 8, and the primary current is 2 amps, so we calculate the secondary current to be 500 milliamps. Now, if you go back through and look at the calculations we performed to determine the primary current and secondary current, and the primary voltage and the secondary voltage, you'll notice that if I decrease the voltage from the primary to the secondary, I can increase the current from the primary to the secondary. And of course, if I increase the voltage from the primary to the secondary, I have to decrease the current from the primary to the secondary. I cannot increase both the voltage and current at the secondary, because that would mean I'm getting more power out of the transformer than I'm putting in, and that just simply is not possible. And the other thing to note with the transformers illustrated in figure 5 and figure 6, they're showing us, for example, 2 turns of wire in the primary coil and 8 turns of wire in the secondary coil. And this is done merely for illustrative purposes, that with a transformer, we're going to have hundreds, if not thousands, of turns of wire in these coils. But you have to understand that, again, for illustration purposes, it would have been very difficult to visualize the operation or construction of these transformers if they had drawn hundreds or thousands of turns of wire in these coils. Now, you'll encounter transformers that are referred to as center tap transformers. And what this means is that there's a connection to the center of the windings of the secondary coil. And of course, this is shown in figure 7. We see both an illustration or a pictorial of a center tap transformer, and you also see the schematic symbol for a center tap transformer. And referring to figure 7, note that all the center tap does is divide the secondary voltage into two equal parts. So if the voltage from T1 to T3 is 24 volts, then the voltage from T1 to T2 would be 12 volts as shown. And of course the voltage from T2 to T3 would be 12 volts also. Now, you will encounter some transformers that have multiple secondary windings. And all this means is there's multiple coils of wire wrapped around the core material to provide voltages for the secondary. And as you can see from figure 8, they do this so that we can obtain or provide different levels of voltage for different circuit requirements. So we can have a set of windings that are called the high voltage windings, and then we've got a set of windings that provide 5 volts and a set of windings that provide 6 volts. And these types of transformers are widely used in the power section of different pieces of equipment. Now, when we derived our equation for the secondary currents in the transformer, we thought of, or we assumed, that the transformer was 100% efficient. And hopefully you can appreciate the fact that this just can never happen. We have no electrical systems. We have no systems that are 100% efficient. There are always losses in every system. Figure 9 shows us a photograph or a picture of a small center tap transformer that's used quite commonly to build a DC power supply. And we have found in the lab that the efficiency of this transformer is typically around 75%. And one thing this tells you is that the ratio of VP to VS is not equal to the ratio of IS to IP, because that equation was derived again with the assumption that the transformer was 100% efficient. Now, this transformer is losing 25% of the power supplied to the primary, and the power obtained at the secondary is losing 25% of this power, and this power is lost in the form of heat. And as we talked about in one of the videos on magnetism and electromagnetism, these losses are due to primarily winding resistance, but also hysteresis, eddy currents, and flux leakage. Now, one thing that is important to understand is what happens to a transformer when we connect a load to the secondary, or the loaded secondary voltage. Now, again, we apply an alternating current source to the primary. Current flows through the primary. It creates a magnetic field that expands and contracts. And if I connect a load to the secondary coil, now current will flow through the secondary coil. And the current through the secondary coil will create a magnetic field too. And note in figure 10, the polarity of the magnetic fields due to primary current and secondary current. And note that the primary current is north to south as shown, and the secondary magnetic field is south to north as shown. Now, what happens here is that the magnetic field created in the secondary actually reduces the energy that's coupled from the primary to the secondary because these magnetic lines of force are going in opposite directions. The larger the secondary current, the greater the magnetic field, the greater the opposition to the primary's magnetic field that is creating the secondary voltage. And man, that's confusing to think about. Okay, so secondary current makes a magnetic field which opposes the primary's magnetic field, which is created by the primary current. And this opposition in magnetic fields actually reduces the secondary voltage. Say that again real fast, John. Okay, well, let's look at some data that we gathered in the lab. Figure 11 shows us, again, some data that we gathered by measuring the secondary voltage and secondary current of a transformer similar to that shown in Figure 9. And note on the graph that when the secondary current is approximately 0 amps, that the secondary voltage is pretty close to 15.8 volts. However, when the secondary current is 1.3 amps, the secondary voltage has dropped to about 12.8 volts. So we see from the graph, the more current that flows through the secondary, the smaller the secondary voltage. And this somewhat agrees with what we talked about earlier this semester, in that every source of voltage has some internal resistance. And as that source supplies more current, the output voltage gets smaller, just like it did with the battery that we tested in Lab 3. Now, one of the metrics we use to quantify this is the percent of regulation. Percent of regulation is simply a measure of the source's ability to maintain a constant output voltage. Percent of regulation, always expressed as a percentage, is calculated as shown. V no load, this is when the secondary current is 0, minus V full load, this is when the secondary is supplying the maximum amount of current it can supply, divided by V no load times 100. And the transformer operation that we looked at in the graph gives us a full load secondary voltage of 15.3 volts and, a no load secondary voltage of 15.3 volts and a full load secondary voltage of 12.8 volts. So this transformer would have a percent regulation of 16.3%. Now, the closer the percent of regulation is to 0, the closer that source is to an ideal voltage source. And again, an ideal voltage source is one where the output voltage stays constant regardless of the amount of current it supplies or regardless of the value of load connected to it. Now, to finish up, talk about transformer ratings. And even though we did calculations, we've discussed up to this point transformers with respect to their turns ratio, we don't purchase transformers according to their turns ratio. So figure 9 shows us again a 115 volt to 12.6 volt center tap transformer that again we would commonly use to build a DC power supply. And if we want to purchase this transformer, we would purchase it according to the following specifications: that the primary voltage is 115 volts, The magnetic system is designed to operate at 60 Hertz. The full load secondary voltage is 12.6 volts, and the full load secondary current is 2 amps. And what this tells you is that we cannot safely apply 230 volts to the primary, that it may cause the insulation around the primary coil's wires to break down. And we certainly couldn't use this in a system that had an operating frequency of 400 Hertz. The magnetic system is designed to operate with a 60 Hertz source. The full load secondary voltage is 12.6 volts, and this is, again, when the secondary current is 2 amps. And the maximum amount of current that we can deliver at the secondary is 2 amps. Now, we can't deliver more current than 2 amps at the secondary of the transformer because, again, there would be too much power dissipation in the device, and the device could be damaged due to excessive power dissipation in the form of heat. Too much current through the secondary windings. Again, P equals I squared times R. And the device could be damaged if we try to, or we ask the secondary to deliver more than 2 amps of current.